So we're going to talk about vectors. We talked a little bit about one-dimensional vectors, and we're going to start talking a little bit about what we would do in 2 dimensions, because the next thing we're going to look at is motion in 2 dimensions. So chapter 3 starts by just talking about coordinate systems and the different types of coordinate systems that we can have. We're going to focus on 2 dimensions. I assume everyone in here, and I've kind of drawn some pictures, knows a little bit about a Cartesian coordinate system. So in this picture right here, we have a Cartesian coordinate system, and we basically have an X direction and a Y direction, and we could pick a particular point in there, and that would represent a point X and Y. So like if I went right here, you know, that would be 2 in the X and 2 in the Y and so on, right? So we've seen some of that before. So one of the things that we are going to have to get used to is going from traditional Cartesian coordinates, X and Y, and going into polar coordinates. And so polar coordinates are represented by an R, it's not working very well, and a theta. And the R is basically the distance from the origin of the coordinate system out to the point in space, X, Y. And the angle is always measured counterclockwise with respect to the X-axis. And so looking at this, and we're going to see this on the next picture, but I could certainly make a right triangle out of this. It's very hard to do on here. Where there would be a side here along the X-axis, and then there would be a side on the Y here that represent those positions. And using that information, and the fact that I have a right triangle and I know how to use sine and cosine, and also just using Pythagorean's theorem, we can find a relationship between polar coordinates and Cartesian coordinates. So as I look at, and I sort of hopefully remember a little bit about right triangles, of course we've got Pythagorean's theorem down here, which basically says a squared plus b squared equals c squared, except in this case our sides are x and y, and our hypotenuse here is this polar coordinate r. And then we can also use our definitions of sine, cosine, and tangent in terms of, you know, sine here is the opposite over the hypotenuse. And so if I define my angle right here with respect to the x-axis, the opposite side to that angle, right? So opposite the angle is the y coordinate, and my hypotenuse is just that polar coordinate r. And then for cosine, cosine is adjacent over hypotenuse. So the adjacent side to the angle is the x side. And so that would be x over the hypotenuse, which is just the polar coordinate r. And then tangent is opposite over adjacent, so y over x. And so we can use those and we can manipulate them so that we can determine either the angles, or we can find the different Cartesian coordinates. So for example, and I'm sure this is on the next slide, if I was given x and y, for example, right, my Cartesian coordinates, then I could use Pythagorean's theorem, and I could find my polar coordinate r, and I could use the fact that tangent of the angle is y over x, so the angle would be the inverse tangent of y over x. So I could determine the polar coordinates r and the angle theta. On the other hand, if I was given the polar coordinates r and theta, then I can use the definition of sine and cosine to figure those out. So if I multiply both sides of the equation for sine and cosine by r, I find that y is just r sine of the angle, and x is r times cosine of the angle. Right. So depending on what I'm given, I can certainly go from one set of coordinates to the other set of coordinates using the fact that I have a right triangle. So here's what basically, it's the same thing that we just had up here. I was just drawing it on that slide. But here's how I could find, going from knowing r and theta, I can find x and y. So, and then I guess, Yeah, and then I have it the other way. Okay, so here's our first example. So if you have the handouts that I gave you, these examples are on the handout with the wording. So this would be for the chapter 3. So we have this, we want to find the Cartesian coordinate x and y that's associated with the polar coordinates r and theta. So the first thing I realize when I look at this is I think about that angle of 233 degrees. So where is that going to lie in terms of my coordinate system here? Is it going to be in the first quadrant, second quadrant, the third quadrant, or the fourth quadrant? The third, right? Because this is essentially 270 degrees. This is 180. This is 90. And this is 0. So it's definitely going to be in the third quadrant. So that tells us something about the sign of the coordinates x and y. So let's go ahead and calculate these. So x is just r times cosine of the angle. So my r value is 5, and then I have an angle of 233 degrees. So my x value turns out to be -3, exactly. And when I find the y value, this is r times sine of the angle. So this is 5 times sine of 233. And my y value turns out to be exactly 4.0, -4.0. So when I put in that angle, it makes sense because if I draw that in my coordinate system, I would have to be along the x-axis -3. So I would be somewhere over here. That's 1, 2, 3 in the negative. And then I would have to go -4. So 1, 2, 3, 4. So I'd be somewhere down here. That's my point, -3, -4. And then my value for r here, this length is 5. And then my angle is this angle right here is 233. So as long as the angle that's given is the angle with respect to the x-axis, then I can always use these relationships. I want to point out that it's possible that you could be given a different angle. So it's possible that if I had a coordinate system like this, maybe they actually tell me this angle right here with respect to the negative x-axis. But you can still find that coordinate because you can make a right triangle, and we're going to do some of this. But you can still figure out what those coordinates are. If this was 5, and I told you that angle, you could figure out the y piece and the x piece going that way. And you just have to realize that it's in that third quadrant. But we'll see some of that. So as I pointed out, yes. So as I mentioned on one of the first couple slides, if I want to go from having my Cartesian coordinates, x and y, and I want to go to polar, I can use Pythagorean's theorem, and I can take the square root of a squared plus b squared, essentially, right? X squared plus y squared. And I can figure out the angle by using the definition of tangent, which is y over x. The angle that we would provide our answer in is measured counterclockwise with respect to the positive axis, as I mentioned. But we have to be very careful when we use the formula for inverse tangent. I don't know how familiar you are with using the inverse functions, but if I plug in numbers and I get out an inverse tangent, I get an angle, what values will my calculator spit out? Anybody know? There's only a certain range that it will spit out. It'll definitely go 0 to 90. Will it give me an angle in the second quadrant? No. Will it give me an angle in the third quadrant? No. It can give me an angle in the fourth quadrant. So basically, when you're using your calculator here, your calculator is going to spit out an angle that's anywhere between minus 90 and plus 90. But we have more angles than just minus 90 to plus 90. So we're going to have to be really careful about how we choose to write down what the angle is. And I picked one specifically as an example so that we could talk about that one. So here we go. Here's a Cartesian coordinate, x and y, that's minus 4 along the x-axis and 2.5 along the y-axis. And here's a picture of representation of that. So essentially, I know that my x side right here, this is 4, and the y side here is 2.5. Yes. So I know that the x part of this has a length of 4 from the coordinate that's given up here, this negative 4. That's telling me that's the x. And then the y is 2.5. There. Yeah, so it is negative 4 if I'm writing it as a coordinate, yes. But the length of that side is just 4. So I can think about it in different ways. But yes, in terms of a coordinate, it is along the negative 4 axis. So I can determine what my polar coordinate is r, because I have a right triangle, and I can use the fact that r is just the square root of x squared plus y squared. So r is equal to the square root of x squared, which is minus 4 squared, plus y squared, which is 2.5 squared. And when I do that, let's see what I get. I get 4.72. I'm going to go ahead and put meters on that because I went ahead and I said that my coordinates were in meters. Be careful when you put this in your calculator, because if you were to put it, and you probably already know this, but I'm saying it anyway, if you put this in your calculator and you don't have parentheses around that negative, it will square it first and then put the minus sign in. You guys familiar with that? You know what I'm saying? So if I were to put this in my calculator, I'm going to write it over here. If I do this in my calculator, it'll give me the wrong result. And in fact, it won't give me any result, because it'll be an imaginary number, because it'll take that negative and it'll keep it negative. So be careful when you're putting it in your calculator. Okay, so if I want to find the angle, I can take the tangent inverse of y over x. Or maybe we start off a little easier. Let's do it from scratch. So let me erase this for a second. So here's the angle that I want. And it's hard to see this, but that's maybe not the best way to do it. I'm going to write it out. So the angle is the tangent inverse of y over x. And that's the angle that we want that I have marked. So this is tangent inverse of my y value is 2.5, and my x value is minus 4. So I put this in my calculator, and my calculator spits out the following answer. Negative 32.0 degrees. Mm-hmm. In the tangent? Yeah, you probably should put the parentheses in there, yes. It's 2.5. It's not negative, it's just positive 2.5. So 2.5 divided by negative 4, and then inverse tangent. You have the inverse tangent on your calculator? So where it says tangent, you do like, what is it, shift or something like that, or second, and that's inverse. So what's the problem with writing it as -32?
It's not starting at 0.
It's not, yeah, it's, well, it could be starting at 0. Well, yeah, okay, so that angle, if I just told you to show me in this coordinate system where -32 is, where would you plot it? In the fourth quadrant, right? It would be, because if an angle is positive, it goes counterclockwise with respect to the x-axis, and if the angle is negative, it goes clockwise. And so this angle right here would actually be represented as this down here. So to get the angle that we want, we have to realize that that number that we get that it spits out is the same thing as numerically this angle right here is 32. Because it's kind of in the opposite quadrant, right? So the actual angle that I want is 180 degrees minus 32. Oops. Which is 148. So be very careful when you're converting between, well, whether you're going from Cartesian to polar or polar to Cartesian, make sure you have the right angle that's shown in the picture. So the best thing to do is when you have a Cartesian coordinate, make sure you identify which quadrant it is, so when you spit out the angle, you know which angle that you should have. And that's going to be important because as we start adding vectors that are not parallel to one another, we're going to have to take that into account. I'm going to wait a minute. I know people are still copying some things down. So. And there are some ways around that with your calculator, but I'm not going to go into it right now. So it's good to just know how to do this. You have to know how to identify what's in what quadrant. Does anybody have any comments, questions? Okay, so so these presentations are broken up into smaller chunks. So I'm going to go ahead and open the next presentation. So I think this is the last slide in this one. So, let's see. Stop sharing. So now we're going to talk a little bit more about vectors, and understanding how to convert these different coordinates is going to be important as we start talking about vectors that are not parallel and to one another. So some of this I already mentioned, so I'm going to go through it a little bit quickly. So in physics, there's basically two ways that we can classify a quantity. It's either going to be a scalar quantity or a vector quantity. So a scalar quantity is just specified by a size with an appropriate unit. So it doesn't have any direction associated with it. Some examples of this are mass, time, temperature, density, pressure, all of those things, even speed and energy, all of those are scalar quantities. We just specify this is how much and we don't worry about direction. A vector is actually something, it's a quantity that describes both magnitude, which is the size, and the direction associated with it. And we already mentioned this. So velocity is a vector, acceleration is a vector. I have to specify how much, how fast am I going, and in what direction I'm going. So some other examples that we're going to come in contact with quickly here is force is also a vector quantity, and momentum is a vector quantity as well. So we've already started to represent vectors a little bit in one dimension. And so just as a sort of a reminder, vectors are represented by an arrow, and the direction that the arrow points is the direction that the vector points. So here I have a vector A, and it's sort of pointing out to the right and up. I have a vector B, which is pointing down. The length of these vectors also tell us something about the size. So I would say here that in terms of the magnitude, vector A is larger in magnitude than vector B because it's longer. If I want to create a new vector C that's twice B, it would be in the same direction as my original vector B. Oops, sorry. Same direction, but twice as long. And I'm not sure if this is physically twice as long in my picture, but this vector here should be twice as long as that one. And so that way we can get some general idea of how big quantities are relative to one another. The representation that we use, typically when we say a vector, we put this arrow over it. We've done that already when we talked about velocity and when we talked about acceleration. In the textbook, they'll use bold. I can't use bold on the board or on the computer, so I will put vector symbols above it. If we're talking about the size or the length of that vector only, then we would just write it without the vector symbol on it, and so that represents just how big this is. Or we could write it as an absolute value, and then I would put the vector symbol over it to represent this. We're talking about the magnitude only. Again, a lot of this is a review of some things that we've talked about already. So a difference between scalars and vectors is distance and displacement. I actually asked this question in class at one point. If I have an object that starts at A and there's a finish line over here at B, then maybe there's some sort of path. Maybe it's a race and they have to get to the finish line and they follow that path. That's the distance that's traveled. But the displacement is just a line that connects the starting position to the ending position. And it doesn't matter what path that you took. And we talked about the fact that the distance and the displacement do not have to be the same value. You can have zero displacement and still have distance covered. So if I end up back where I started, my distance would be some value, but my displacement would be zero. Oh, I thought I fixed this, but I didn't, but that's okay. All right, so as we're adding, so we want to know how to add vectors, because eventually we're going to be interested in adding velocities together or subtracting velocities when we talk about acceleration. So this is the general way that we would add vectors. So the first thing we have to do is we have to choose some sort of scale. So we're just doing this sort of graphically at this point. We would draw the first vector in A with the appropriate length and in the direction specified. Now I have the extra piece on here. I thought I animated it correctly, but I didn't, so it's already there. Pretend it's not there for the moment, so pretend this is not here. And the first thing I would do is I would draw in my first vector. So I may need to use a ruler, I may need to use a protractor, and I would put that vector A in with the length and an angle. And then I would draw the next vector with the appropriate length and direction, and I would start it at the tip of the first vector. So I connect vectors head to tail. So my next one I would put at B, or at the tip of A, and I would draw it in. It's usually a good idea just to make yourself another little mini coordinate system when you draw that, and then you can draw the vector in appropriately in terms of what direction it points. And then the resultant, or the addition of A plus B, is a vector that starts at the tail of the first vector and goes to the head of the last vector that was connected. So we're going to use this, and we're going to look at how we can add these. So I could do this graphically if I gave everybody a ruler and a protractor and I said, all right, we're going to use this conversion like we would on a map. You could draw this picture with these angles, and you can figure out what this would be in terms of its length and the angle that it makes here. But drawing things graphically is not the best way to do things, because we can make errors and there's some uncertainty in terms of reading our rulers and so on. So we need to find a better way to do this. The other thing to keep in mind that it doesn't matter how many vectors you add together. So if I add A plus B plus C plus D, as long as I keep connecting them head to tail, The resultant vector is a vector that starts at the tail of the first vector and goes to the head or the tip of the last vector. Adding vectors is also commutative, so you can do it in any order you want. I could have done A plus C plus B plus D, and I can't do it on here, and it would still give me this same exact resultant vector right here. One thing to keep in mind is that if I were to draw on here another, I'm going to go ahead and draw on here another vector. If I draw A like right here, those are both A. It doesn't matter where that vector starts or anything. So even if I drew it up here, as long as I drew it the same direction and the same length, all three of those are still the same vector A. Doesn't matter where you put them. So you can move them around a little bit, and that's fine as long as you keep their size and their direction the same. One of the things that's that we're going to have to do is we're going to have to subtract vectors, because acceleration, as we know, is just the final velocity minus the initial velocity. And all of those terms are vectors, right? Acceleration is a vector, velocity is a vector. So I'm going to need to be able to subtract vectors. Well, subtraction essentially works similar to addition. What you have to know is that if you have a minus sign in here, so A minus B is the same thing as A adding to it a vector that's minus B. Because, you know, if you add a negative number, it's the same thing as subtracting numbers. But we have to know how to write a negative B. A negative, all that does to a vector is it changes its direction by 180 degrees. It's going to come up here, but I'm going to go ahead and draw a picture. So if I have a vector here, for example, I'll just call it something else. I'll call this a vector C. The vector minus C has exactly the same length, and all I do is I switch the direction that it points, and that's the negative of the vector. So I can subtract vectors by just adding vectors together with a minus sign in front of one of those vectors. So here we go. Here's my vector A. I'm going to temporarily draw in vector B. Okay, there's my vector B. I want to add A to a negative B. So here's my vector B. If I want negative B, I have to draw the vector exactly the same length, but exactly in the opposite direction. So there's minus B. So I have A, and then I'm adding to it, connecting to the tip of A, vector minus B, which is exactly opposite of B. And then my resultant vector is a vector that starts at the tip of my first vector and goes to the head of my last vector, which happens to be a minus B. Somehow I switched the color here, sorry about that. So that would be my A minus B that points along here. We're not going to probably draw a lot of pictures where we subtract the vectors or add them, but we will need to know how to do this, and I'm going to show you how to do it from a mathematical standpoint. There's another method that we can use, and that method, the other thing we can do is we can take vector A, so there it is right there, and I can draw in and I can draw vector B so that it is at the tail of A. So before I had A, and then I connected B to the tip, and then I drew in negative B. This is another method, and if you've taken physics before, you may not have done it this way, but this is something else you can do. Once you connect them both at the same position at their tails, then A minus B points from the tip of B to the tip of A. And if you look at this line here for A minus B, and you look at this line here for A minus B, they are exactly the same length. They are the same direction, and so that's another method you could do it. if you think about adding vectors head to tail, what I'm doing here is I'm taking B and I'm adding to it A plus a negative B. Well, B plus A plus minus B is just A. That's all that's left. And so here's my A. That's my result.
If you have like A plus B plus negative B plus C.
But you have a whole bunch of them,
Yeah.
right? Let me see if I can discard. All right, so here I can make one, right? So you want one that is, just tell me what you like, A plus B minus C or something like that? Plus B minus C.
Plus B C.
Plus D?
Yeah.
Okay. So one of the things I would probably do, if this was one that I was going to do, I would say the order doesn't matter, because remember, it's commutative, addition is commutative. So I would say I'm going to rewrite this as A plus B plus D to start with, if I was going to try to draw a picture of it, and then I would subtract C. It might be easier to do it that way. If I were doing multiple vectors, I would not use the second method that I had mentioned where you connect them to the tail. I would just use the method where I would write this as A plus B plus D plus a minus C. Yeah, I'd probably do it that way. So let's assume I had, here's A. So I would draw my A in. Maybe my B goes like this. All right. Maybe my D goes this way, right? And then maybe my C kind of goes at a weird, maybe my C goes like this. Here's C. So I'm doing it with a dotted line because I don't want to add C to it. I want to add minus C. So I've connected them all head to tail, but I want to add a negative C. So I would draw something like this, making sure it's the same length, like that, right? And now I need to find my final answer, which is connecting, starting at the tip or the tail of my first vector. I got to draw a line from here up to the head of my last vector, like that. I'm not sure I can draw this as a straight line, but it should be a straight line along that. So this would be A plus B minus C plus D. I mean, it doesn't matter what order because of that. Does that make sense? Mm-hmm. Say that one more time. Oh, yes, 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 yes. Thank you. This is a minus C, yes. We're not going to, I mean, we will draw pictures to see what's going on, but we're going to actually use a method where we can actually put some numbers in and calculate things exactly, because, you know, you try to draw things to scale and it doesn't work particularly well. All right. All right, so drawing these pictures, again, even using rulers and protractors, is not the easiest way to get an answer, and it's not very exact. So we've got to find a mathematical way of doing this. And the way that we do this is by using something called vector components and unit vectors. So if you've had physics before, and even if you haven't, it's fine, you've probably heard about components of vectors, like X components and Y components. Just out of curiosity, has anybody heard about unit vectors? Some of you have heard about unit vectors. Okay, all right, so a lot of you, perfect. All right, so this method of components allows us to take vectors that are pointing in different directions and add them together and then find out what that resultant or that end result of adding those vectors together is, what its length is, and what its angle is. So it turns out any two-dimensional vector, doesn't matter what it is, can be represented as the addition of two perpendicular vectors that are called the components of the vector. So I think, oops, I'm going to go ahead and draw them on here. It's on the next slide, but I'm going to draw it on here anyway. So what that means is that because we know that vectors connected head to tail can give us a resultant vector, that means that I can write this vector A, so here's my vector in my coordinate system, as the addition of two vectors that are perpendicular to one another. And so the way that it works is I want to create two vectors that when I add them together and when they are perpendicular to one another, they give me that resultant vector, that A. So the way that I would do it is I would go along, so I drew in my dotted line there along the y-axis from the tip of my vector A. And now I can connect two vectors head to tail to equal that vector A. So I can start at the tail and I could go along the x-axis, and that is a vector that I'm calling AX. That's this piece right here. And then I can add to it a vector AY that goes here. And that's this piece. And so if I add AX to AY, connecting them head to tail, the end result is this vector A. Now, we already talked about these coordinate systems and how there's a relationship between the X and the Y pieces and sort of the polar versus the Cartesian. And so this looks very similar to that, where I've got X and Y, sort of, they're not coordinates, but they're vector positions. And then I've got this length from the origin out to the end point and an angle. So we're going to be able to use some of those things that we talked about. So if I were to give you what the value is for the length of my vector and the angle of my vector right here, if I gave you those two things, we could figure out what those component lengths are because I have a right triangle here. And because of that right triangle, as I look at the angle, the piece that's opposite to that is the y-axis. So I know that sine of the angle, which is the opposite side, would be AY over the hypotenuse, which is A. And I know that cosine of the angle is equal to the adjacent side, which is the x side, so AX over the hypotenuse, which is A. So these are all just lengths, they're numbers that would represent those sides of the triangle. And so if I multiply in these two equations here, if I multiply by A, I find that the x component of a vector can be found by taking the hypotenuse, the length of the vector, times cosine, and I can find the y piece by taking that vector and multiplying by the sine. You might say, well, why do I care about doing that? And we'll see why that's important here in a little bit when I want to add vectors together. Similar to converting between Cartesian and polar, here, if I were to, this is what would be given here, would be the length of my vector and the angle, right? And I could figure out the components. On the other hand, if I gave the components, I could figure out the length and the angle. So we could kind of work the other way as well. So in this particular case, if I was given AX and AY, and I knew what those values were, I could use the fact that I have a right triangle, and I could figure out what the length of my vector is using Pythagorean's theorem. And I can figure out the angle by using inverse tangent. So in this case, tangent is equal to opposite over adjacent. Here's my opposite side, and here's my adjacent side. Here. So this is where we're getting AY over AX. So we can use that to determine the angle, just like we were doing with our coordinates. So similar to our coordinate positions, the components of the vectors, the x and the y components, can also be positive or negative depending on where they fall in our coordinate system. So here's a representation of when they will be positive and when they will be negative. So if AX and AY are both positive, that means my vector is in the first quadrant. And if my x component is negative and my y component is positive, it means it's in the second quadrant. So like a picture of this one here would be a vector that points somewhere like this. Okay? And if I had to draw a picture of how I would resolve that vector into components, or how I would find the components, I would have to start at the tip. I would have to go along the negative x-axis and the positive y-axis. And so that's why this is negative and that one is positive. In the same regard here, both of them would be negative because the vector would point down in the third quadrant. And it's just a good idea to just keep in mind how you would have to draw the components to get there. You'd have to start here, go over, and then down. And so both of these are negative. And then the last one would be over here somewhere. And then to draw that, I would have to go along the x-axis and then the y-axis. So this one is plus and this one is negative. So get in the habit of sort of drawing a little picture to see what's going on, because it'll help you visualize when you have to deal with the angles. So the sign of the components depend on the angle, right? So it depends on where you are in terms of your coordinate axes. But the angle also depends on the sign of the component. So that works in reverse, right? So based on where those, whether your x and y are positive or negative, will tell you what angle that you're actually at. Okay, so we want to have a way of describing the fact that a vector is pointing along the x-axis or pointing along the y-axis or possibly even pointing along the z-axis. And so we define these things called unit vectors. And unit vectors, because we use the term unit right here, this means length of 1. That's what unit is representing here, a length of 1. So if I multiply anything by 1, I still get back the same thing, right? So if I had a vector that pointed along the x-axis, like we said AX, that's a vector, that's a component of the vector that we saw that points along the x-axis. What that means is that I could write this as just having some length associated with it. So this is the length of the vector. Ooh, that did not work out well. Sorry. No. So this is the length of the vector. And then I could multiply this by some direction. So I'm going to multiply this by a direction along the x-axis. And as long as that direction along the x-axis has a length of 1 associated with it, then it's simply specifying direction. And so these unit vectors are vectors that have a length of 1 that point along each of the respective axes. So a unit vector I points along the x-axis. So here's my I right here, right? It's pointing along the x-axis and has a length of 1. J is a vector that has a length of 1 and it points along the y-axis. And then K points along the z-axis. So that means that my AX that I had here as a vector, I could write as having some length associated with it and a direction along the x-axis, and the direction along the x-axis is the I direction. To specify that these are unit vectors and not regular vectors that are bigger than 1, we use little hats on top of them. So what I don't do is I don't write a unit vector like this, right? That's not what I do. Instead, I write it with a little hat, and that tells me that the length of that vector is 1. So x, y, and z form a set of mutually perpendicular axes, and so I, j, and k point along those axes, and so they are also mutually perpendicular to one another. Trying to be careful of the time. Okay, I'm going to say this last thing, and then we come back tomorrow. We're going to do a number of examples. So I already said this on the last slide. So my AX is the same thing as just saying that it is some length, and then it has a direction along the x direction, which is represented by I. My AY is just some length multiplied by the y direction, which is j. And I could do the same thing with z. So if I had something along the z direction, it would be AZ along the z direction. So basically, I'm able to take this vector A, and I can write it as the addition of AX and then AY in the j direction. This is the same thing as saying that this is the sum of the vectors along the x direction, the y direction, and the z direction. We're really not going to do much with the z, but all right, I know we went through a lot today, but we'll do lots of examples when we come back, all right? And the next homework is due on Wednesday, but by the time we complete this stuff, you'll be able to do that.